All right, so remember, complex numbers are really just numbers that can be written in the form of a plus bi, where a is the real part of the number and b or bi is the imaginary part. And we're looking for roots, but roots are just the solutions of an equation. So on the imaginary plane, the solutions of complex numbers can be written also in polar form. So a plus bi would be a way to write a complex number and graphed where a, you would move to a units on the real axis or the horizontal axis. So this would be a. And on the imaginary plane, you would move up to b. And so this point on the imaginary plane would be a plus bi. And I don't really need that paren, a plus bi. So I can graph using the standard form or the form we're used to working with complex numbers, but I can also write complex numbers in polar form. When I write a complex number in polar form, it looks like z, which just represents, it's a way of saying a complex number. So z equals r cos theta plus I times sine theta. And that would be written in polar form. And the way we get that, or use that in polar form, is if you know that a point on the complex plane, and let's just use a plus bi, is located here, well, we have a r value, or what could be considered a radius to get, or a distance from the origin to that point. We have a horizontal component, which is generally written as r cosine theta, and that's on the real plane, or the real axis. And then we have a vertical component, which would be written as r sine theta, but that's imaginary. So we have an I times r sine theta. If I pull the r or factor the r out, I'm left with exactly what I wrote up here, which is z equals r cosine theta plus I sine theta. All I've done is factor the r out of the polar description for the location of this point. Now let's kind of work with it a little bit. So we have a really important theorem called de Moivre's theorem, and not being French, it does not roll off my tongue easily, but it's spelled D-E-M-O-I-V. Yes, I'm having to look at this. V-R-E with an apostrophe S because it's possessive. So de Moivre's theorem. Yikes, that was the hardest part of the theorem, frankly. It basically says that if I square both sides of this, I can find the power of a complex number by raising it to the nth power, obviously, and just taking the same formula, that would be equal to r to the nth times cos theta plus I sine theta to the nth power. Okay, that seems crazy obvious, and it really is, and it's super easy to use, obviously, but a better use for this theorem is an extension from it, which is a way to find the roots of complex numbers. So we can look for the roots of complex numbers using the formula, the nth root of our complex number z is equal to r times, the nth root of r times the cosine of theta plus 2 pi k over whatever n is, plus I times sine theta plus 2 pi k over n. And I know at first sight it looks just a little bit tricky, but it's really just a bunch of pluggy-chuggy math, my favorite kind of algebra. All I have to do is find various values of k that I can plug into the formula and give me the root. Even that sounds tricky, but it's not, because you're going to choose k values always starting with 0, and then 1, and then 2, and then keep going, choosing one integer after another until you get to the n minus 1th k value. So if you're looking for the square root, all you need is the 0 and the 1, because the square root would be a 2. 2 minus 1 is 1. I would stop with just 2 values. It couldn't be any easier than that to find nth roots. And we're going to do an example. We're going to do a real tough one, actually. But it's a very famous root to look for. Cubed root of I. So we want to find the cubed root of I, which means we know there are 3 roots. I have to use 3 different values of k to find my 3 roots. Well, there are my 3 different values of k, 0, 1, and 2. 2 is 1 less than the root of 3, so I know I'm just going to plug in those values. First, I have to find out what r is for I, for the number I, and you should always start with a picture in these. You should always graph them on the real and imaginary axes. So first, let's start with the number I and write it as a complex number. Well, we have 0 real parts plus we have 1 imaginary part. If I plot this, I'm not going to go anywhere on the real axis, but I'm going to go up to 1 on the imaginary axis. And so this right here represents my my graphed form of I. So let's write it now in polar form, which means we need to know what the radius is. And so the radius of a complex number is, since we're dealing with an axis, right? It's not a Cartesian plane where we have a real horizontal and a real vertical. It's a complex plane where we have a real horizontal and an imaginary vertical, but still we do exactly the same thing. We know where that point is. We want to find the radius. Okay, let's be clear. I already know the radius is 1, and I know you know the radius is 1, or that the length or magnitude or the distance from 0 of our point on the imaginary plane is 1, but we're going to pretend like we don't know, and we're going to use the math that we have to use to find it when the numbers are more complicated. So we do exactly what we've done 1,000 times before, and what is alluded to in this picture is I'm going to find the magnitude of r by taking the distance I've traveled on the horizontal or the real plane, so my real component squared plus my imaginary component squared, and I'm going to take the square root of that, trusty old Pythagorean theorem, and so I end up looking for the square root of 1 squared, which is just 1. So I know that my r value, so the third root or the cubed root of 1 equals 1, and so now I know what I'm going to plug in out front, and then I just have to go and figure these other values out. Let's start with theta. Well, theta in a polar coordinate, written as a polar coordinate where r would be 1 and theta would be the degrees, 90 degrees, we're talking about 190. So theta in this case is 90 degrees. I'm going to work with 90 degrees is so much easier to do in degrees than pi over 2. So I'm actually going to not use 2 pi. I'm going to use 360. I'm going to work in degrees instead of radians. It's certainly allowed, unless you're told otherwise. Do whichever comes easily to you in the time, in the moment. So first, I like to figure out what's inside first. You'll see in a second how that makes the whole job so much easier. So I'm going to set it up. First, I'm going to set up for my k equals 0, and I'm going to work down here for when k equals 0 to find one of my roots or one of my solutions, and then I'm going to work with k equals 1 to find another root, and then I'm going to work with k equals 2 to find my third root. And we're expecting only 3 roots because I'm asked to find the cubed root, so I'm expecting 3. So first, let's work inside here. When k equals 0, then the internal inside of the parentheses is 90 degrees plus 360 times 0 divided by n is my cubed root, right? N is 3. And get a little more room here. I'm going to lose my formula, but I remember it. And hopefully you've written it down so you'll be able to use it. So this just equals, well, I'm going to divide 90 divided by 3 is 30 degrees. And 360 divided by 3 is, well, 360 divided by 3, 360 times 3 is 0 divided by 3. So I'm actually done with that one. That was pretty easy. And then when k equals 1, I have 90 degrees plus 360 times 1 divided by 3. Still again, just looking for inside those parentheses. 90 divided by 3 is 30 degrees. And then 360 divided by 3 is 120. And if I add these together, I get 150 degrees. Then k equals 2. Inside the parentheses, I'm going to end up with 90 degrees plus 360 times 2 divided by 3. I don't see any reason to change the method I'm working in. 90 divided by 3 is 30 degrees. And then 360 divided by 3 is 120, but the 120 still needs to be multiplied by 2. So that's 30 degrees plus 240, and that's 270 degrees. So that means one of the roots can be found looking at an angle in the first quadrant of 30 degrees and finding my sine and cosine values in my formula. The other root can be found by looking in the second quadrant at a reference angle of 30 degrees where I have 150 degrees from 0. And my last root I'll be able to find at 270 degrees, which is the same as 3 pi over 2. I guess I should label all of these. And so all I need now is to use my roots formula to find the actual roots. So out front I have r cubed, which we already know equals 1, so I'm not even going to write it down. And then inside I'm looking for the cosine of all of this, which means I'm looking for the cosine of 30 plus I times the sine of all of this, so the sine of 30. In this second case, I'm looking for the cosine of 150 plus I times the sine of 150. And in the third case, for the third root, I'm looking for the cosine of 270, which we already know is 0, so that's going to be easy to work with, plus I times the sine of 270. So let's break them down. The cosine of 30 is root 3 over 2. In the first quadrant, it's positive, plus I times the sine of 30 is 1/2, and in the first quadrant, it's positive. Next, I have the cosine of 150. Again, it's root 3 over 2, but in the second quadrant, the cosine is negative, plus I times 1/2, and all students, the sine function is still positive. And then for the last root, I have the cosine of 270, yay, is 0. We always love zeros. Plus I times the sine of 270 is just negative 1. And I can write that better as 0 plus negative, oh, that wouldn't be better, would it? That would be very elementary. 0 minus I. So these are the 3 cubed roots of I. In the same way that the cubed roots 3 times 3 times 3 equal 27, I could multiply these 3 roots, that would be the first, then the second, and then the third. If I distributed them into each other, I should, and I expect to, end up with I. So let's do one more example. I hope it goes quickly because I'm running out of time, I think. So we want to find the 5th roots of negative 2 minus 2i. So the first thing is we notice that z, our complex number, is negative 2 minus 2i. We should always draw a picture, see where it lives. And so on my real plane, I have -2, or on my real axis, I'm looking at -2, and on my imaginary axis, I'm also looking at -2. And so at this point, this is what I'm looking for. I'm looking for the polar coordinates for this point, which means I need an r and I need a theta. First thing I want to find is r. I'm going to use the Pythagorean theorem as always. I want to find my horizontal component, which is -2 squared, plus my vertical component, which is also -2 squared. And so that's the square root of 8, 4 plus 4, which equals 2 times the square root of 2. So that's my r value. My theta, I imagine, because my horizontal and vertical components are the same, that this is probably a 45-degree angle, reference angle from pi in the negative direction. But we don't always have something so easy to see, so we want to use the inverse tan function of -2 opposite over -2 adjacent. So we're looking for the inverse tan of 1, and that is, let me move it here, I'm pretty sure I'm going to want extra room. And that is pi over 4, which is exactly what I expected. So my actual angle, though, isn't pi over 4. The actual angle is 4 pi, 5 pi over 4. Okay, now I have my r and I have my theta, 5 pi over 4. I'm going to work in radians this time. No special reason, just kind of fun to shake it up every once in a while. And I think I'm going to need this time to go ahead and find my fifth root of r. So the fifth root of r means I'm looking for the fifth root of 2, root 2. Okay, that's pretty ugly. I'm pretty sure I'm going to want to use a calculator. So I think first I'll put in 2 times the square root of 2, and it's probably going to give me an exact value. Yep, that's okay. So I want to take this, and I'm going to raise the whole thing. Well, I better use parentheses just to be safe. This calculator can be a little finicky about that. Okay, and I'm going to raise the whole thing to the 1/5 power. Okay, exact value, well, not exact value, approximate value, 1.23. All right, let me move this for a second. And now I'm going to put together my formulas. First, I want to find the part that goes inside of the parentheses. I'm sure you have notes that you can be looking at. So I know that, my k values. Let's talk about k values. I want to use k values 0, 1, 2, 3, and 5 minus 1 is 4. I'm expecting there to be 5 fifth roots, 5 things to multiply together to get -2 minus 2i, and I have 1, 2, 3, 4, 5 integers that will give me that in the distinct roots formula. I'm not going to do them all, mostly because of time. I think I'll do 0 and 2, just for the fun of it. But first, let's find for k equals 0, let's find the inside or the guts of that formula. So our angle is 5 pi over 4 plus 2 pi times k, which is 0 in this case, over my root, which is 5. So that's 5 pi over 4 divided by 5. So I end up with pi over 4 as the angle I want to work with. So now I can put it back into my formula. I have my fifth root of r, which is 1.23 times the cosine of pi over 4 plus I times the sine of pi over 4. 1.23 times, well, the cosine of pi over 4 is the square root of 2 over 2 plus I times the square root of 2 over 2. So if I had an exact value out front, I'd probably stop here or just distribute the exact value in. But since I have a decimal, I'm going to go ahead and pull up my calculator and find the decimal for the entire number. And I think you'll see, yep, I went ahead and set the problem up just because of time. So root 2 over 2, whoops. Root 2 over 2 times 1.23 equals 8.69 la 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 la. So let's just say 0.869 la 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 la. So let's say point or 0.87 maybe. I think I said the wrong number multiple times. I promised to write it down correctly. 0.87. I'm going to say 0.87 plus 0.87i, and because I have the same thing to multiply into, I get the same value both times. So this is one root, one of the fifth roots. The other one, I'm going to go ahead and do it. I know the video is getting a little bit long, but I think it's useful to see it more than once. It is pluggy chuggy math, but it can be a little bit confusing thinking of all the moving parts that you have to deal with. So this time we have 5 pi over 4 plus 2 pi times 2 divided by 5. So this is the guts before we start to do the work on the formula. So I have 5 pi over 4. I think I'm going to separate them out and use my 5 cancel for that one. Plus, this is 4 pi over 5. I think it might be easier to keep them separate. Pi over 4 plus 4 pi over 5. Yeah, I think it might be easier just to keep it this way and do the math on my calculator than to try to combine these two fractions into something sort of ugly. So now this is the angle I'm going to work with. So let's write it out. 1.23 times the cosine of pi over 4 plus 4 pi over 5. And luckily our calculators have good functions for handling those. And then this is plus I times, you gotta love electronic paper, the sine of all that ugliness. Pi over 4 plus 4 pi over 5. Okay, so now on our calculator, all right, so I went ahead and did this off camera again, just because, or off recording, because no need to have you watch me push buttons. First, I put this into my calculator. I got 21 pi over 20. Then I took cosine of this 21 pi over 20 times the 1.23, and I got 1.22. Or I guess I could say 1.23 plus, or in this case, it's going to be, yep, plus. I did it for the same thing for sine, distributing across into the sine, and I have 0.07. And then just to be sure, even though I felt pretty confident with the work I did by hand, I went ahead and put the whole thing in again. I put this, the top part up here, in, and it is indeed 21 pi over 20. So I'm pretty confident that this is my root, or my second or third root, I guess. This would be the first root. And then this would be the second, third root. And you could, of course, do this, though why would you want to? But you could do this to find all 5 roots of the complex number -2 minus 2i.